So good evening to all. I hope my voice is audible. Can anybody respond?
Yes, sir.
Okay, fine, thank you. So welcome to the another NPTEL live session of the NPTEL course Heat Transfer. So today this is our fifth session. So we'll be discussing about the contents related to the week five topics. So let's have a brief recap about the week five topics discussed in the lectures. So mainly, it was a flow over a flat plate where we discussed about the momentum and thermal boundary layers. So we have uh, derived the governing equations, and from there we have used the similarity solution or Blasius equation to find out the uh, expression for boundary layer thickness, that is hydrodynamic boundary layer thickness, and also from that we have calculated uh, the shear stress that is acting on the flat plate, and from that we calculated the coefficient of friction. From the heat transfer perspective, uh, we uh, we did the similarity analysis or similarity uh, analysis and found out the expression for the heat transfer coefficient, so which was a function of the Reynolds number and Prandtl number. So then we discussed, or then we derived the expression for Nusselt number over for a for the situation of lower flat plate. Then we discussed about the turbulence, turbulence, turbulent flow over the flat plates, and and the additional stresses like Reynolds stresses that is happening on, or that is comes out in the time averaged or the average Reynolds time average Reynolds of situations. So these were the main topic of discussion for week five. So in this session, we will discuss about some simple questions based on these topics. So let's get started with the first question. So an engine oil at 100 degrees Celsius at a velocity of 0.1 meter per second flows over both surface of 1 meter long flat plate maintained at 20 degrees Celsius. Determine the velocity and the thermal boundary layer thickness at the trailing edge. So I will give you some time. It's just a direct substitution of formula. So I'll just give you 2 3 minutes for you to try this out, and after that I will solve the question for you. So it's like we have a plate, flat plate, and the oil, engine oil at 100 degrees Celsius and u infinity, that is velocity 0.1 meter per second, is flowing over. It's not like on the one surface. It is clearly mentioned that it is flowing over both the surfaces. That is on the top surface and the bottom surface. The the flow is happening. So in both surfaces, the boundary layer will be both velocity and thermal boundary layer will be formed. So this plate is at 20 degrees Celsius. So because of the temperature difference, the thermal boundary layer will be formed, and and also the velocity boundary layer, hydrodynamic boundary layer will be also formed. Both boundary layer will be formed on both sides of the plate, but it will be identical. The boundary layer on the top means thermodynamic boundary layer on the top surface, and the bottom surface will be identical. Like that, the hydrodynamic boundary layer on the top and bottom surface will be identical. So, so if you got the answer, you can just comment it in the chat box. So before that, I will just ask you one question. So here the Prandtl number is 1081, that is greater than 1. So which will be means uh, which will be larger, means the thermal boundary layer thickness or the velocity boundary layer thickness will be uh, greater, means the momentum diffuses faster or the thermal energy diffuses faster. So this I explained in the last class. So if I draw, so which one will be red, sorry, which one will be green and which one will be the blue line?
The hydrodynamic boundary layer will grow faster, sir.
Yeah, so the green will be hydrodynamic boundary layer. So this will be thermal boundary layer. So I already mentioned in the last class, I think I specified this as engine oil or the high viscous oil, engine oil as an example for this case. So for Prandtl number is equal to 1, what will be the situation? Which one will be higher?
So both equal, sir.
Yeah, so the hydrodynamic and the thermal boundary layer will be same. So have you got the answer? Okay, so I will just start it. So we already in the lectures is already derived that the thermal bound, sorry, this is the hydrodynamic boundary layer thickness. We are asked to find out the trailing edge. So at any location, it is 5x divided by root REX, right? So this is the length L. Here we are asked to find out a trailing edge. So delta L is equal to 5L divided by root REL. Okay. So what is Reynolds number at L? So mu infinity L divided by mu. U infinity is given as 0.1. Length is given as 1 meter. Viscosity is given 86.1 into 10 raised to minus 6. So what is the Reynolds number here? So I am getting this as 1161.44. So this is a, as it is for, what is the critical Reynolds number for a flat plate? It's 5 into 10 raised to 5. So as this is less than 1, we this our assumption, this is for laminar boundary layer. So our assumption for laminar boundary layer is flat. Okay. So delta L is equal to 5 into length is 1 divided by root of 1161.44. How much is the answer? So the answer will be 0.14673 meter. Okay. So this is the hydrodynamic boundary layer. So for Prandtl number greater than or equal to 0.6, we have the expression that is thermal boundary layer to velocity boundary layer or hydrodynamic boundary layer is equal to Prandtl number raised to minus 1 by 3. Okay. So it's an approximate expression. It's approximately equal to Prandtl number raised to minus 1 by 3. So we know the hydrodynamic boundary layer. So Prandtl number is given, that is 1081 raised to minus 1 by 3 into 0.14673. So what is the answer? Anybody calculated? So it will be near to around 0.2 0.0143 meter, right? So means it's like we can approximate we can approximate as it is. So in competitive examinations you can take some trick, and also so as it the options are already given, so you can find a close match. Means as it is as it is 1081, you can approximate it as 1000 raised to 1 by 3, so it will be so it will be 10, so divide by 10, so approximately equal to 0.014. So, okay. So we can see the difference between the thermal boundary layer and the velocity boundary layer. So the thermal boundary layer is 1 by 10th of the velocity boundary layer. So the correct answer is option A. So let's move on to the next question. So this next question is also based on the first question. It is question 1. So we have to find out the local heat flux and the surface shear stress at the trailing edge. Okay. So at the trailing edge, we need to find out what is HL and what is tau WL. Okay. So how to proceed is we already know it is already derived the expression for heat transfer coefficient, right? Or we can say Nusselt number. That is from heat transfer coefficient only, its Nusselt number is coming. So nu at x, any x location is 0.332, Reynolds number raised to 1 by 2, Prandtl number raised to 1 by 3, right? So when HL is equal to, what is Nusselt number? Is equal to HL by K, right? So if you substitute, if you rearrange it, how will it become? K by L 0.332, Reynolds number raised to half, Prandtl number raised to 1 by 3. So what is HL? HL is K is already given 0.14. L is given 1 meter. 0.332. Reynolds number we already find it out, which is 1161.44 raised to half. Prandtl number is given. Okay. So if you calculate this, you will get the answer as 16.1 watts per meter square Kelvin. Okay. So what is heat flux? Heat flux at line L is equal to HL T surf or T infinity minus T surface. Right. So it is 16.1 into what is T infinity? 100, and T surface is 20. So it's 100 minus 20. So the answer will become 1288.17 watts per meter. So this is the local heat flux at the trailing edge of the flat plate. So the first part of question is over. Second part is we need to find out what is the shear stress tau W. Right. So we also derived the expression for tau W in the class. Means we know CFX, that is the friction coefficient, is equal to 0.664 divided by root RE, root REX. What is tau W? Or we can say, so the friction coefficient CFX is equal to tau WX divided by half rho U infinity square, right? So from that we can easily calculate what is, we are asked to find out the trailing edge. So tau WL is equal to CFL into half rho U infinity square. Okay. So we can substitute the values, that is 0.664 by root What is REX? We already found out. That is 1161.44 into half rho u infinity square. Right. So rho is rho it is given. How much is rho given us? Rho is 864. So 0.664 divided by root 1161.44 into half times rho is 864 into u infinity 0.1 square. So can you please calculate this? What is the final answer for shear stress? The trailing edge. Okay, you can do the calculation later. So it will be around 0.0842 Newton per meter square. Okay, so this is the heat flux and the shear stress at the trailing edge. So next question is also based on is a continuation for the first part. So we need to find out what the total drag force and total heat transfer per unit width of the plate. So we already found out what is the shear stress, right? That is tau W, we already know. Or it's not the tau W of the entire surface, it is the tau W at a particular location, that is the trailing edge we have found out in the previous question. Now they are asking about the total drag force and the total heat transfer coefficient. So we need to find out the average shear stress, right? Or average shear stress over the surface, tau W average. So it's already means it is already derived in the class that tau W is equal to 2 times tau W at the leading edge. So for upper face, so here we should means be very careful. Here the question it is already told that in both the surface flow is acting. So in both the surface drag force will be both the surface will be experiencing the drag force. So we need to consider the both surface. So for upper surface, we know that is force Fs, shear force is equal to average shear stress into the area. The area, so the surface area, right? So the surface area, I am taking the length or the it is asking a question to take the width of the plate as 1. So I am taking the width of the plate of 1 and the length of the plate as L. So it's already given what is Fs is equal, L is already given 1 meter. So Fs is equal to tau W bar, right? So for both the surface, this is acting. So total drag force will be twice this, right? So F total is 2 times Fs, which is 2 times tau W bar. So we already calculated, or which is we can write 4 times tau W at L. So we already calculated what is tau W at L. 0.0842. So please calculate this and say what is the total shear stress that is happening. Sorry, total force that is happening experienced by the flat plate. So this will comes out to be 0.3368 Newton. So this is the force that is experienced by this flat plate on both the surfaces. That is the total drag force it is experienced. So next we need to find out the total heat transfer. So for just like means we already find out what is heat transfer coefficient at the trailing edge. So we know the average heat transfer coefficient over the length is 2 times HL. That is 2 times the heat transfer coefficient at the trailing edge. So I'm not going for the derivation. You can refer to the lectures how this 2HL comes. So we are asked to find out what is the heat transfer, right? So Q is equal to H surface area into Ts minus T infinity, or means here it is T infinity minus Ts. So here it is average heat transfer. Just like previous case, in two surfaces, both the surfaces will have heat transfer. So it will be 2 times HL. So we already found what is it is like 4 times HL area, just like per unit width 1 and into the length L. So into 1 into 1 and to 100 minus 80. It is 4 times what is HL, heat transfer coefficient. We found out as 16. 16.1 into, sorry, this is how much? 80 or 20? It's 20. So this will be 80. So what will be the answer? So the final answer will comes out to be, this is Newton per meter width, right? Is 5152 watts per meter. Thus we are considering the unit length. So this much watts per meter is the heat transfer. It is happening both sides. Okay. So I hope this question was clear. It's a direct substitution of the formulas. So we will go to the next question. So a steel strip emerges from a hot rolled section of steel mill at a speed of 20 meter per second, and temperature of the this steel strip is 1200 Kelvin. Its length and thickness are 100 mm and 0.03 meter. 100 meter and 0.03 mm we can write. So the its density and the specific heat is given. So according for the heat transfer from both surfaces and neglecting the radiation and strip conduction, determine the time rate of change of strip temperature at a distance of 1 meter from the leading edge and the trailing edge. So you can consider this as you can cut this with one at a distance of 1 meter from the leading edge. So that is the question. Okay. So we have a hot strip. So this is the steel rod. It is coming out from a rolling rollers. So usually we will consider the as the strip is moving, right? In this case, strip is moving, air is constant. But we can do because we can recreate the same situation when the strip is stationary and the air over this is flowing at the same speed, right? So it is both are equivalent. So we can consider that the air over this is moving at a speed of 20 meter per second, and the temperature of the steel is 200 Kelvin, 1200 Kelvin, and the thickness of the steel it is given as, can write as delta. It is 0.003 meter, and this length of the strip is given as 100 meter. So And what is the temperature of the air? Mm. So the temperature of air we can consider it as 300 Kelvin. So I think it's not mentioned in the question, but you can consider it as 300 Kelvin. 300 Kelvin means like atmosphere, that is 27 degrees Celsius. So, so what we need to find out is this. I am taking this as the leading edge. So from here, at a distance of 1 meter, we need to find out the rate of change of temperature at this point. That is our question. Okay. So, and we are asked to neglect the strip conduction effects and radiation effects and all. And we need to consider only the convection that is happening from the strip. And I'm let the length, that is the width of the strip, I am assuming it as W. That is the width means the length that is measured into the plane of this paper. That is width of the strip. I am consuming it as W. So, so there is no heat generation. There is no. So what is our general? We are going back to the first classes. That is E dot in minus E dot out plus E dot G is equal to D E system divided by dt. Okay. So I am considering these as this this point, that is at at 1 meter from the leading edge, a small elemental control volume of dx. Okay, of dx of length dx and thickness delta and along the and also width w. So there is no energy that is coming in. This is zero. There is no heat generation. That is zero. So only minus E dot out is equal to the rate of change of the system. So minus E dot out is equal to rho Cp dt divided by dt at x, or at x is equal to 1 meter. Rho v, that is mcp dt. So rho v rho v cp dt, right? So what is E out? Oh, the only heat transfer mode that is happening is like by convection. So minus q convected at x is equal to 1 meter should be equal to rho v cp dt by dt at x is equal to 1 meter, right? So what is q dot convected? That is q dot convected, convection is equal to h, that is area of the strip. H, what is the area? That is delta into the length w, that is width, into the length I am considering dx, right? Into t infinity minus or ts minus t infinity. And also v is equal to what is, so this is volume, sorry. So the area of heat transfer is how much? So here I am only considering, so you may be getting doubt that the both surface we should consider or not. So unless not specified, you can consider only one surface. Okay. Okay, no. You have to consider both surfaces. It is in the question, it is mentioned we have to consider heat transfer from both the surfaces. Okay, so here we need to consider both the surfaces. So what is the area of heat transfer? So the top part, which is the area of hydrogen, this is W and this is dx. So it is 2 times W dx, right? That is the heat that is convecting away from both the surfaces. So this is Hx 2W dx, ds minus d infinity would be equal to rho V I am writing as W dx and delta Cp dt by dt. So this dx cancels, W cancel out. So the what we need is dt by dt at x is equal to 1 meter. It is minus hx ts minus or ts minus t infinity divided by rho delta Cp at x is equal to 1. So this is what we need to evaluate. So next is simple. I am writing this here. Okay. So Hx we already know, that is 0.332 Reynolds number raised to half, Prandtl number raised to half, 1 by 3. So the Reynolds number is V u infinity x divided by mu. So that we can calculate. I am not calculating it. If you calculate it, you will get it as all the values I have given. That is mu, v, Prandtl number, everything. So if you calculate the Reynolds number, it comes up to be 2.61 into 10 raised to 5. So which is a laminar, which is comes in laminar region. So okay, so if you find it out, Hx is equal to, it will comes out to be 8 point, sorry, this is not Hx, this is the Reynolds, sorry, this is the expression for, we need to multiply with K and L to make it Hx. So the Hx will be 8.28 watts per meter square Kelvin. Okay, so we got Hx. So everything we got, that is Hx we got, Ts and T infinity we already given in the question, and rho delta Cp all we can write. So it is at x is equal to 1 meter minus 8.28 into 1200 minus 300 divided by rho is, how much is the rho given? 7,900 times delta is given as 0.003 times Cp 640. So if you calculate this, you will get the answer as minus 0.982 Kelvin per second. Okay, so this is the rate at which the temperature decreases at a location 1 meter from the leading edge. Okay, so we have to consider heat transfer from both the surfaces. So if it is not specified, you can, mostly it will be specified in the cases we need to consider. But if you are simply given a flat surface or something, I'd say you can just go for the one side only. But please try to understand the applicability of the question. So means whether we need to consider both the surfaces or not. So based on the situation, you need to check whether we need to take heat transfer from both sides, unless it is specified. If it is not specified, so this is the temperature at which at that location the temperature is decreasing. So next question is, you need to find out the distance from the leading edge where the heat transfer, where the cooling rate is minimum. Okay, so let's check whether somewhere the turbulence, so laminar to turbulence transition happens. So we will check what is the critical Reynolds number for this situation. That is not critical Reynolds number at which location this transition happens. So the critical Reynolds number for a flat plate is 5 into 10 raised to 5, which is u infinity x divided by x critical divided by mu. So x critical you will get it as 5 into 10 raised to 5 into mu. You calculate it, you will get. So the mu is given in the question, that is 76.4 into 10 raised to minus 6 divided by u infinity is given how much? 20 meter per second. So you will get the answer as 1.91 meter. So the total length of the steel plate that is mentioned is 100 meter, right? So okay. So in some distance, not in the some distance, at a distance 1.91 meter from the trailing edge, the boundary let or the flow transfers from laminar to turbulent. So you will study that maybe in the coming classes. The heat transfer coefficient in the laminar region we already studied is proportional to x raised to minus 1 by 2. And heat transfer coefficient in laminar in turbulent region is proportional to x raised to minus 1 by 5. So in turbulent region, there will be heat transfer will be enhanced because of the eddies that is forming because of the turbulent nature of the flow. So in turbulent region, both heat transfer and momentum transfer will be enhanced because of the eddy formation or turbulent natures of the turbulent nature of the flow. So the point where, so we know when the boundary layer grows, the heat transfer coefficient will be reducing along the distance x, because so the distance over which, so the thermal boundary layer will act as a resistance to heat transfer. So when we in laminar region, so at a point where this laminar to turbulent happens is the point where the least heat transfer coefficient happens, or we will get the least heat transfer coefficient, or the least heat transfer coefficient means, or when the heat transfer coefficient is minimum, we can say that the heat transfer rate will be also minimum at that location. So the distance from the leading end at which the minimum cooling rate is achieved is actually the critical, is the point where the laminar to turbulent transition happens, and it is the point where the Reynolds number is critical Reynolds number, that is 5 into 10 to 5. So in this question, it is 1.91 meter. Okay. So let's go to the next question. So air at atmospheric pressure and temperature of 25 degrees Celsius is in a parallel flow at a velocity of 5 meters per second over a long flat plate that is heated with a uniform heat flux of 1250 watts per meter. Assume the flow is fully turbulent over the length of the plate. Calculate the plate surface temperature at the trailing edge of the plate. Okay. So this question, no, you can avoid this step. You can find out whether it is laminar or turbulent. Okay. With the Reynolds number calculation, you just find out whether if the flow is laminar or turbulent. If it is laminar, we can use the laminar flow correlations or the equations, or if it is turbulent, we can use that equation. So don't consider this sentence. You just calculate what is the Reynolds number or the Reynolds number at the trailing edge of the plate. Okay. So let's get started. So it's like we have a plate. So we are heating it using a coil, so that it will produce a heat flux of 1250 watts per meter square. over the surface. The air is flowing with a velocity 5 meter per second at 25 degrees Celsius. So its length is given as 1 meter. So we need to find out what is the, this is leading edge and this is trailing edge. What is TS at the leading edge, right? So UW is equal to HL, that is heat transfer coefficient at the trailing edge, into, or it is heat flux, no need of area, that is Ts at L minus T infinity. So TSL is equal to simply Q double dash by HL plus T infinity, right? So how will you find of HL? So as we have done a lot of example in the previous, a similar type in the previous example questions. So it's, we already know 0.0332 Reynolds number at L raised to 1 by 2, Prandtl number raised to 1 by 3. So we need to check whether it is laminar or turbulent. So it is U infinity L by mu. So what is U infinity? It's 5. Length is given as 1. Mu is, it's asked to take us 18.76. So if you calculate this, you will get the answer as 2.67 into 10 raised to 5. So it's in the laminar range. So we can use the laminar correlations, right? So it's 0.332 into 2.67 into 10 raised to 5 raised to half. Prandtl number is given as 0.703 raised to 1 by 3. So what is the answer? Yes, let me calculate. 2.65 into 10 and raised to 5. So times 0.332 minus. This is so the answer to the, if you calculate this, K is 0.028 divided by, you will get it as 4.328 watts per meter square. Okay, this is the heat transfer coefficient at the trailing edge. So just now, just we need to substitute the values. That is, what is 250? It's already given 4.328 plus what is T infinity? T infinity is 25. That is so the answer will come out to be, so the temperature at the trailing edge, if we give for this conditions, will be 313 degree Celsius. Okay, so it was a simple question. So let's go to the next question. So aerofoil with a characteristic length of 0.15 meter and a surface temperature of 325 degrees Celsius is placed in air at 35 degrees Celsius and with free stream velocity of 100 meter per second. The rate of heat transfer from the aerofoil is found out to be 1600 watts. If a second aerofoil with a characteristic length of 0.3 meter and a surface temperature of 425 is placed in the airflow, same airflow, at 37 degrees Celsius with a velocity of 50 meters per second. Determine the rate of heat transfer from the second aerofoil. This is our question. Assume steady state conditions in both aerofoils are geometrically similar. So, we need to find out Q from the second one. Okay, second aerofoil. So first aerofoil I'm considering as case one, and second aerofoil is considering as case two. So if we calculate the Reynolds number of first one, that is Vd by or VL, its characteristic length is given. So U infinity 1 L1 divided by as it is as the airflow means as it is going through same airflow at the same temperature, that is both temperatures are same, 37 degrees Celsius, 37 degrees Celsius, but different velocities. The same fluid, the viscosity will not change. That is kinematic viscosity will not change. So it will be same in both the cases. So U infinity is given as 100 to L 0.15 by mu. That is 15 by mu. Reynolds number of 2, U infinity 2 L2 by mu. Same kinematic viscosity. It is given as 50 into L2 is point. So both Reynolds number, that is Reynolds number of 1 and Reynolds number of 2 are same. So both situations or both condition, both aerofoil will have the same Reynolds number, right? As the fluid property, so Prandtl number, if you say Prandtl number is equal to mu Cp by K of the fluid. So as the both fluids are same both aerofoil conditions situations, the temperature of air is not changing. That is, it is kept at a temperature of 37 degrees Celsius. So viscosity will not change, specific heat of air will not change, thermal conductivity will not change. So Prandtl number of 1 and Prandtl number of 2 are same. So as we know, the average Nusselt number is a function of only Reynolds number and Prandtl number. It's not the function of the characteristic dimensions. I'm saying about the average Nusselt number, not the local Nusselt number. So the average Nusselt number is a function of Reynolds number and Prandtl number only. So as Reynolds number and Prandtl number is same for both the cases, we can say that the Nusselt number of first case and Nusselt number of second case is same, are same. Okay. So we can write H1 L1 divided by K. Both are same. So the K is same in. So K is a property of the fluid. So it is same. H2 L2 by K2. So no, there is no need of K2. It's K. Okay. So this is one expression, that is H1 L1 is equal to H2 L2. Now, what is Q? Q is equal to H. I am not considering about, no, it is saying that the surface area of the aerofoil may be assumed to be directly proportional to the characteristic length. So Q is proportional to H L delta T. Or if you write Q1 by Q2 is equal to H1 L1 by T S1 minus T infinity H2 L2 divided by T S2 minus T infinity. Right? So if you calculate this, you will get, we need to find out Q2, right? So it is, so everything is given. So we can just calculate. What is the surface temperature of TS1 3M 325 minus infinity is 37 divided by second case 425 minus 37. So Q1 by, so it will be, yeah, this is 325 minus 37, 425 minus 37. So we will get it as Q2 is equal to this will cancel because H1L1 is equal to H2L2. We already write. So it will be Q1 divided by 0.7422. So Q1 is already written as 1600 divided by 0.7422 means what, 0.7422. If we calculate this, it will come out to be 2155.56 watts. So the closest answer is the answer D. So I hope this was clear to you, the question. So this kind of questions you can expect in this competitive examinations where you can solve it very fast. So in this case, the Reynolds number per se as a fluid is same and both are air, and the temperature of the air is also same. The Prandtl number, the properties of the fluid won't change. So Reynolds number and Prandtl number are same. So the total or the average numbers, Nusselt number will be same. So just equating the Nusselt number, you can find out what is the heat transfer rate from the second layer of fluid. So this was our last question for today's session. So I hope if anybody has any doubts, I think I explained everything, every question, every question. So if you have any doubts, you can just ask. Otherwise, you can leave the meeting. So see you. Thank you for attending this session, and our next session will go next Monday, 6 to 7. So see you in next session. Thank you.